Hello everyone, I am D. Venkatarvin and this is the presentation on my review of homological product codes by S. Bravyi and M. B. Hastings. So this is the flow of presentation where first we look at the motivation of studying quantum LDPC codes, then we look at the boundary operators and homological product from homology theory to an extent that is required to understand the presentation that follows. Then we look at the hypergraph product code, then we look at the results of applying homological product to two random codes. So LDPC codes are codes that have a sparse density parity check matrices. So good LDPC codes are those LDPC codes that have encoding rate and distance in the order of n. So why to study these LDPC codes? There are many advantages of LDPC codes, and there are important class of codes to study because they are extensively studied in the classical field and and they have a very simple fault tolerant syndrome readouts simply because they have a each stabilizer is associated with a very less number of qubits to get the syndrome, and LDPC codes with distance growing faster than log of n have constant error threshold for stochastic error models. So here you can see a list of family of codes with parameters k, d and w. Here w is weight of parameter, which can be seen as a parameter that measures sparseness of the code, sparseness of the parity check matrix of the code. So you can see that surface codes which are known to be implementation friendly in the real life have a weight of 4, which is a constant. But you can see that surface codes suffer from distance scaling as it is only O of root n. You can see that homological product codes have an improvement over hypergraph product codes in terms of distance scaling, and they also have an improvement over good quantum codes in terms of sparseness of the parity check matrices. But you can't call homological product codes as good quantum LDPC codes because the sparseness is not O of 1, it is still dependent on the n. So a boundary operator is a mathematical object associated with the chain complexes in the homology theory. To simplify things for us, we see a boundary operator dou as a square matrix which satisfies dou square equal to 0. One interesting thing is that we can define a CSS code using these boundary operators. So we can see the format of a stabilizer generator matrix using a boundary operator as shown below. One can also see that the condition for CSS code where hx into hz transpose equal to 0 is also satisfied with this boundary operator by using that dou square equal to 0 in the definition above. One reason to map CSS code to boundary operator is to leverage the existing knowledge and properties in homology theory to extract the parameters of the code. Here you can see how the parameters of code is calculated using the homology theory associating boundary operator to it. Homological product is again an operation where it takes two boundary operators as input. Let's say boundary operators dou1 and dou2 acting on spaces c1 and c2 respectively, and it outputs a new boundary operator delta, which is given by the equation given below. So delta acts on space c1 tensor product c2. We can see that delta square is also 0, which states that the delta is indeed a boundary operator. So now the parameters of the CSS code associated with this boundary operator delta is derived from the homology theory as shown here. N is n1 into n2, k is k1 into k2, derived from Kenneth theorem. W is less than or equal to w1 plus w2, and distance is given by the inequalities shown here. So hypergraph product code is a specialized form of homological product code. Actually speaking, hypergraph product codes are defined before this paper. So strictly speaking, homological product codes are generalization of hypergraph product codes. So hypergraph product codes involves two steps. It first takes classical codes and derive boundary operator from them, and then it uses homological product to multiply, or it uses homological product to get a new boundary operator from the boundary operator derived from classical codes. So first it starts with the classical code n, k and d. In deriving boundary operator, it involves adding dummy stabilizers and ancillary qubits. Let's say in this example, it adds a dummy x stabilizers. Then the parity check matrices associated with Z-type stabilizer generators A and parity check matrices associated with X-type stabilizer generators B will take form as shown below. So the boundary operator that is then generated is of the form dou equal to B transpose into A. We can see that row space of dou is row space of A and row space of dou transpose is row space of B, which is exactly how it is intended to be. So one must also note that this code has dx equal to d and dz equal to 1. So dz is 1 because the dummy stabilizers we add will have only one qubit associated to it. So the next step is we'll take two classical codes with parameters n1 k1 d1 and n2 k2 d2 and add and treat them differently in the sense that for one code we add x-type dummy stabilizer generators and associate the existing classical parity check matrix to the z-type stabilizer generators, and the further for the other code we'll do the exactly opposite. So the parity check matrix is associated with the z-type x-type stabilizer generators and we'll add z-type dummy stabilizer generators. After doing this, we get the boundary operators associated to these modified codes. Let's say dou1 and dou2, and then uh, by applying homological product to this dou1 and dou2, we'll get new code. Let's say delta again. So the parameters of the delta code is as shown here. N is n1 cross n2, k is k1 cross k2, w is less than or equal to w1 plus w2. Coming to the distance here, we can see that the distance for the distance case, the lower case and upper, the lower bound and upper bound are coinciding, which means that dx will be d1 of x without loss of generality, and dz is d2 of z. So d, which is minimum of dz and dx, will be minimum of d1 of x and d2 of z. So you can see that the distance is not scaled, though encoding scaled accordingly, encoding rate scaled accordingly. So this is what we saw in the table which listed family of codes where hypergraph product codes are not good at distance scaling. So we see that hypergraph product code showed that we can get almost good quantum LDPC codes if we start with good LDPC codes. The almost part is because it doesn't scale in the distance parameter. So in the remaining part of the paper, the author showed that the homological product of two random codes drawn from an ensemble, which necessarily need not to be a LDPC codes, will be a good code. So here the term good code is those codes uh, where homological product gives scaled distances, unlike hypergraph product codes where distance is not scaled. So the author rigorously proves that homological product code of two random codes drawn from ensemble of codes drawn from ensemble which need not to be a QLDPC codes will be a good code with high probability using some statistical arguments and other mathematical arguments. So to conclude, homological product enables us to construct a high distance sparse quantum codes by combining two small distance codes. And homological product of two random stabilizer codes provide us the first example of good quantum codes with sublinear sparseness. Thank you.